Hello, today we are going to take a look at the basics of vectors. Now, our objective here is to use our structure vectors to perform some basic operations. We'll be finding our dot products, our angle between vectors, some scalar multiplication, but first we need to talk about what vectors are. A vector is a quantity that has magnitude and direction. So we see a vector right down here. We've got this line V. All vectors have a starting point, which is our initial point, and an ending point, which is a terminal point. All of our vectors are going to have the notation of a lowercase italicized letter, typically V or W or U, although I'm going to try and not use U and V in the same problem when I make them because, here's your U, here's your V. They look a little too similar for things to be clear. Every vector, our magnitude is going to be the length of the vector, and then the direction is just how far it gets rotated, identified by this angle theta here. This should look very familiar from when we were looking at polar coordinates. We've got our standard vector that we will kind of write in polar coordinates, where we've got our v theta, we've got our magnitude and our direction, but then this is going to be called component form, where it's written with these arrow brackets and an x and a y because we have our horizontal component and our vertical component. Converting between these two different forms is going to be critical to doing some application with these later on in the unit. Now, with our vectors, they all do have that length, that magnitude. That's the same as our radius in polar, and our direction, which is the same as our theta in polar. In dealing with a lot of these vectors, we can move them around on the coordinate plane a little. Let's look at this vector over here, which has an initial point at 0, 5 and a terminal point at 3, 7. And what we're going to do to be able to work with these better is use a position vector. So a position vector is a vector that has the same magnitude and direction as our original vector, but its initial point is at the origin. So essentially, all it's doing is taking this vector and moving it down so it has the same magnitude, same direction, same horizontal and vertical components, just starts out at the origin. And that is going to help us when we're working with different vectors, like when we have multiple ones in some application problems, and will also help out because we can refer to this vector as our horizontal component of 3, because we go 1, 2, 3, and then our vertical component of 2. So we can refer to this as 3, 2, even though it started up here. It's going to be a lot easier to work with as 3, 2. Unit vectors, not going to show up a ton here, but if you go on and take some later math courses, they will show up there, but that just has a magnitude of 1. Same direction, but magnitude of 1. Now, sometimes we will be given a vector in its points. So here we are given vector CD. Sometimes we'll have a vector in this form where C is our initial point, and then D is our terminal point. In this case, our vector CD is going to have a horizontal component of, well, what's our distance between 1 and 7? It's going to be 6, and we can always calculate it. This as our terminal minus our initial. So 7 minus 1 is equal to 6, and then -2 minus -3. I like writing these out because dealing with negatives, sometimes it helps to have the paper help you out with this. So it'll end up being -2 plus 3, which will be 1. So we can write that vector CD as 6, 1. In another example, let's take a look. We've got this CD is going to be 7 minus -8, and then 2 minus 10. So we'll have 15 and then -8. Sometimes, like with this number 4, we'll already be given this in component form, and some of the problems will need the vector in component form. Sometimes we will need it in just dealing with our magnitude and direction, like in number 5. Now, if we have this in with our magnitude and direction, well, we need to think back to when we were dealing with polar coordinates. So if we just write this with our square brackets, let's do a better square, write this with our square brackets, and we just need to convert this to our rectangular form, which gives us our horizontal and vertical components. So x is equal to r cosine theta, and y is equal to r sine theta. So we've got our x component is 75 cosine of 135 degrees. And with vectors, unlike with our complex and polar, we are going to be working in degrees, not radians. So make sure to switch your Desmos and switch your calculator for that. Then we've got 75 sine theta, which is 135 for our y component. I do not have access to a calculator right this second, so you would put that in your calculator or Desmos to calculate the components. Why we care about this is going to be evident later in our application problems. We need to just go over a bunch of these smaller basics with vectors here. A few different types of multiplication we are going to talk about. The first one is going to be scalar multiplication. A scalar is just going to be a constant that we are looking at here. So if we start with this vector v, a scalar is going to be written as something like 1/2 v or 3v, where we're just taking a constant, multiplying it by a vector. The problem will look something like this. We will have an actual vector in component form, and if the vector is not in component form, we will need to write it in component form. So in this case, we have f, and we need to find -9f. So what we end up doing is taking -9, multiplying it by our x component, taking -9, multiplying it by our y component, and our resulting products are going to give us the resultant vector. The resultant vector is just our answer. It's what happens after we do whatever operations we're doing to the vector. So this, you're essentially just distributing the number. So scalar multiplication ends up a lot like distribution. Sometimes we can have scalar multiplication and addition or subtraction of vectors. So for example, with 18, we have u and b as vectors. We have -u minus b. Well, what I like to do here is write these separately. -u is equal to -5, -7. -b is equal to 2, -12. and then negative, if we have it as negative u plus negative b, all we do is add the x components, and that will give us our resultant x component. So negative 5 plus 2 is negative 3. Do the same thing with our y components. Negative 7 plus negative 12 is negative 19. And there we go. It looks kind of like it should look, and would make sense to look. So it works out with the scalar multiplication, with the addition and subtraction. You can, as long as it's in component form, you can combine them. Now, let's take a look at another type of multiplication. Our dot product, our input is two vectors, whereas our scalar multiplication, our input was one vector and one constant, and our output was a vector. Our input for dot products is going to be two vectors, and our output, our result, is going to be a constant. And our dot products are really important for finding the angle between vectors, which we'll talk about soon. And that's really it. So we need to just be able to calculate these first and then deal with finding the angle later. So our dot product is the sum of the product of the horizontal components and the product of the vertical components. All right, so if we look at this definition here, it gives us V is equal to AB and U is equal to CD. So our dot product, which we write out as a dot, like V dot U, is going to be equal to the sum, so we're adding some things, the horizontal components, the product of the horizontal components, product of the vertical components. So product is multiplication, so it's A times C plus B times D. So you're taking your x components, multiplying them, taking your y components, multiplying them, adding them together. So let's take a look here. Our dot product of u and v. Again, I do not like using u and v in the same problem because they do look similar. Our output's going to be a constant, and it's going to be product of our x components plus product of our y components. So we have 0 plus 27. So our dot product is going to be 27. Let's take a look at one more example. So we've got u is equal, or our dot product is equal to 4 times negative 1 plus 1 times negative 3. So we have negative 4 minus 3. So our dot product is going to be negative 7. There are a few other ones with dot products that you can practice. Now, we've got our angle between vectors. For any two vectors, and we're talking 2D vectors here, another video we'll talk about three-dimensional vectors, our cosine of theta, and remember we're in degrees, is equal to this. Our numerator is our dot product, and then our denominator is our product of the magnitudes. So our magnitude of a vector is shown as absolute value because that's really what absolute value is. It's a magnitude, it's a distance from 0, and that's the notation we're going to use. So what we'll do, let's look at this first one with u and v. So our dot product is 27. And we need all of the parts of this problem before we go on to put it in the calculator to find our angle between vectors. So our magnitude of u, well, how do we find our magnitude? If we've got a vector, that's our hypotenuse of a right triangle. So we've got an x component, we've got a y component. Our magnitude is the hypotenuse, so we can use the Pythagorean theorem. So what we do is take the square root of our x component squared plus our y component squared. So 2 squared plus negative 3 squared. So we've got 4 plus 9. So it's the square root of 13. We need to do the same thing for our magnitude of v, which, well, this one's just 9 because 0 squared is 0, negative 9 squared is 81, but then we need to take the square root of that, which just gives us 9. So we can write out our angle between vectors. So our cosine of theta is our dot product divided by the product of the magnitudes. So 9 times the square root of 13. We can factor out a 9. So our denominator is just going to be 1 times the square root of 13. Numerator is going to be 3. But in order to find theta, we need to take the cosine inverse of both sides of this equation. So we have theta is the cosine inverse of 3 divided by square root of 13. So that is what you would put in your calculation device in degrees. Let's take a look at another one. So for 34, we've already found our dot product. Let's find our magnitudes. So our magnitude of u is going to be the square root of 4 squared plus 1 squared. So it's going to be the square root of 17. Then our magnitude of v is going to be the square root of negative 1 squared. And watch when you're putting this in the calculator because it's negative 1 squared. Not that we need to put negative 1 squared in the calculator, but if you put it in as negative 1 squared, order of operations, you'll get 1 squared is 1, multiplied by negative 1 and get negative 1, but it needs to be positive because anything squared, our output's going to be positive. Well, except I, but we're only working with real numbers now. So in this case, it's going to be the square root of 4, which is 2. It's not the square root of 4. It is going to be the square root of 10. So when we're setting this up, we've got our cosine of theta is our dot product of negative 7 divided by the product of the magnitudes. And the way that multiplication and square roots work, when we rewrite this and what we're putting in the calculator with our cosine inverse of a fraction, we can put both of these numbers under the square root. Like when we're doing multiplication or division, we can do 2 smaller square roots, 1 bigger square root with the same operation underneath. So you would put in cosine inverse of negative 7 divided by the square root of 170 to find the angle between these vectors. So you've got some practice on here, and then next lesson we are going to take a look at how we apply these vectors and how we're going to use the properties we've talked about today. Thanks for watching.